Hi, today I present to you Neural Attention-Guided Pruning for Unified Multimodal Resource-Constrained Clinical Evaluation. 2 billion X-rays are generated globally every year. These are large DICOM files requiring massive expensive storage. This makes adopting powerful AI tools impossible for most resource-constrained clinics. The core bottlenecks are the enormous download times for data and the long training times for models. Our work is designed to solve these specific problems. The key here is that we don't just have images, we have powerful image report pairs. For every chest x-ray, a radiologist provides a written report with their findings. We use these pairs to train our model on critical downstream tasks like detecting pneumonia or other pathologies. This research prompts us to explore two key questions. How can we minimize the required storage space for large multimodal X-ray datasets without losing on its clinical utility? And how can we use the multimodal nature of the data to govern the unsupervised data reduction process? So what about existing approaches? They have major limitations. First, model-centric approaches focus on speeding up a single task. The problem is you always need the original full resolution image for any new analysis, so they aren't flexible or task agnostic. Then you have conventional compression like JPEG. It makes files smaller, but it's clinically agnostic. It doesn't know what's medically important and can easily destroy critical diagnostic information. Before our main method, let's cover a key preliminary, the cross-attention mechanism. First, we would divide the entire image into several different patches of same size and would like to find how each patch correlates with the text within the radiology report. For that, we would use the image embedding for each patch and text embedding for each token, and then we would calculate the query key and value pair as similar to how we would do in any other cross attention mechanism. And then finally, using that, we would find the cross attention scores using the query embedding and key embedding, and this is the matrix which is very important for us to finally get the values of the cross correlation. This slide shows the rationale for our pruning method. We ranked image patches for their average cross-attention scores across two major datasets, MIMICCAI and CheckSpert Plus. The graph shows a sharp drop-off for both, proving that only the small handful of patches are truly important for diagnosis. This result validates our core strategy. We can safely discard the majority of the image data and focus only on the critical regions. Our framework comprises of 3 steps and we will go through each one of them one by one. The first step of our framework, that is dual role of decoder for pruning image and text generation. First, we take the X-ray image and pass it through the SWIN-based encoder. This converts the image into a set of compact numerical representations or patch embeddings. We also add the positional encoding to each and every patch so that our model is aware of the global positioning of the patch. Then these embeddings go to a decoder, and this decoder we use to generate the chest X-ray report. We fine-tune this decoder on thousands of radiology reports from the MIMICCAI dataset. Its job is to learn how to generate an accurate text report directly from the image embeddings. This initial training is crucial because it forces the model to deeply understand the link between clinical findings and the visual data. The second step of our framework, that is image text cross attention score based pruning. First, we would convert the image patch embeddings into an image graph where each node represents the patch and edges connect the neighboring patches. This is how the visualization looks for this graph. Then we would calculate the cross attention scores between the image and the text so that we could use these scores to prune the image graph. We would only keep the nodes which have very high attention scores. Our final step is unified text image graph enhanced diagnostics. To avoid storing the ground truth text, we use the fine-tuned decoder to produce the text. We create a knowledge graph out of this text which would look like this using the Biomed VLP CXR BERT model, which is an entity and relation extraction model for our case. To unify these two modalities in the graph format, we would directly connect the nodes with highest betweenness centrality in these graphs. This helps us do message passing across modalities while having minimal overhead. Finally, we do message passing using message passing neural network to enhance the embeddings and then predict the downstream task using the classifier. Moving on to the datasets and experimental setup. We use two image report pair datasets, MIMICCI-XR and CheckSpurt Plus. For both fine-tuning and downstream tasks, we followed this split for training our model using 5 random seeds. For report generation, we use two benchmarks, RGRG and CBT2 Distill GPT-2. Both are strong baselines evaluated on this task, with RGRG being published at CBPR 2023. For pneumonia detection downstream task, there are very few multimodal models that have been benchmarked on our datasets and are suitable for our tasks. These are CheckSmed and RMT. For radiology report generation, our model performs better than both the benchmarks. It can be observed that this increase in performance mainly comes from the fact that our framework is capable of handling any size of image and not just constrain it to the fixed image resolution like other models. Even after pruning the image, our model still performs comparable to other benchmarks for both the datasets. For pneumonia detection, our framework has been evaluated in 3 different settings. First is no pruning, second is when we compress the images and use the text from the original dataset, and the third one is that when we use the text generated from our decoder instead of original dataset. We can observe that there is an increase of 5% in the AUC score if we fairly compare these models. However, even after pruning, our model still performs comparable to other baselines. The pruning percentage for both the datasets are also very high. Even when the pruning process didn't take into account the supervision signal from the downstream task, our model still performs better, proving its task agnostic pruning. We also conducted ablation study for our neural framework. It can be observed that as we prune the image further and further, after a certain point, the area under the curve drops off for both original text as well as generated text, which is around 97% mark for the MIMICCI-XR dataset. If we just evaluate our model using only the image graph, then as we increase the pruning percentage, the AUC drops off to completely random guess. Let us reflect on the strengths of our framework. It handles multimodal data and is extensible to several other modalities. The overall data production process is also task agnostic, meaning that no downstream task involved in pruning. The percentage pruning ratio is also very high with minimal loss in performance, and even post pruning, the report generation quality is good. Potential research direction include extending to temporal modalities which are present in MIMIC 3 and MIMIC 4 datasets, and also evaluating on several other pathologies. Thank you for your attention.